Okay, in this problem, we're asked to find V0 in the circuit below using both Thevenin's and Norton's theorem. And when deriving a Norton equivalent circuit, we're going to break the network to the left of the 4K resistor. So first, we're going to go and utilize our problem-solving strategies for applying Thevenin's theorem. And what we'll do is we're going to go and identify our load here. We're going to remove that from the circuit. We're going to calculate the Thevenin equivalent. Okay, remember our Thevenin equivalent is an open circuit voltage series with a Thevenin resistance. Then we'll hook up our 2 kilo ohm resistor to Thevenin equivalent and find V0. Okay, so let's now remove the 2 kilo ohm resistor from the circuit and find the open circuit voltage. So when we remove the 2 kilo ohm resistor, here's our circuit now, and we're going to find the open circuit voltage. And if we look, we apply Kirchhoff's current law here. There's 2 milliamps flowing there. There's 0 out there. Okay, so the voltage across this resistor is 6 volts. So we have 2 milliamps times 3K. Now the voltage across this resistor is 0 because the current's 0. So now if we apply KVL around the outside here, we'll have V0 is equal to minus 6 plus 12 equal to 6 volts. Okay, so there's the first part. Now we need to find the Thevenin resistance, and if we look at our circuit, we only have independent sources. So one way we can find the Thevenin resistance would be to go in and turn these sources off. So if I turn a current source to 0, I would replace it with an open circuit, and if I turn the voltage source to 0, I replace it with a short circuit. So my resulting circuit then is this. And if I notice, looking at the circuit here, our Thevenin is 3K plus 4K, which is 7 kilo ohms. So our Thevenin equivalent circuit then is a 6 volt source, 7 kilo ohm resistance. Now we hook our 2 kilo ohm load back up, and then we now solve for V0, and we can do that by voltage division. So V0 is 6 times 2K over 2K plus 7K, and that's 6 times 2 ninths, which is 4/3 of a volt. Now we were also asked to find V0 using Norton's theorem. So let's go back to our circuit here with Norton's theorem. Now what we're going to do is we're going to find a current source in parallel with a resistance. That's a Norton equivalent. Now we were asked to break it at this point in the circuit. Okay. Now we broke it at the 2K resistor for the Thevenin theorem. We could do the same thing here, but let's look and see what happens if I break the circuit here now. Okay. So we're going to calculate the short circuit current. So when we break the circuit at that point, notice how simple our circuit becomes now. And you say, well, how's this so easy? Well, let's apply Kirchhoff's voltage law around the outside here. The voltage across this resistor by Kirchhoff's voltage law is 12 volts. It has to be. So by Ohm's law then, the current flowing through this resistor is 4 milliamps. And then if we apply Kirchhoff's current law here, then I short circuit is 4 milliamps minus 2 milliamps equal to 2 milliamps. And then if we find the Thevenin resistance for this configuration, if we turn this source off and this source off, basically turn this to 0, it's an open circuit, turn this to 0, it's a short circuit, then our resulting circuit is that. So our Thevenin is just 3 kilo ohms. So by breaking it where we did, we simplified the calculation some. So now our Norton equivalent circuit is this. You have 2 milliamps parallel with a 3K. Here's where we broke the circuit. 4 kilo ohms, 2 kilo ohms. Here's V0. Now I want to calculate the current I1 using current division. So I1 is 2 milliamps. We want the current through this outside loop, so we have 3K over 3K plus 6K. Gives us 2/3 of a milliamp. So then V0 is 2K times 2/3 of a milliamp, and it gives us 4/3 of a volt.